Hey, my name is Matt Gallo, and I'm going to be showcasing the malware analysis Capstone project, which was completed by Erik, Grinn, Jackson, Eyink, Jourdyn, and myself. To start, this project had two primary objectives. The first was to establish an isolated virtual environment consisting of multiple virtual machines connected to a common virtual network, and use this virtual environment to document the steps taken and results of both static and basic dynamic analysis on 2 to 3 key pieces of example malware. The output of this project was a thoroughly documented report of how to accomplish these two objectives. And what made this project compelling was that it offered practical, real world cybersecurity experience in a controlled environment, helping to develop valuable technical skills in malware analysis, virtualization, and safe lab practices that are directly applicable to industry roles. And at this time, I'm going to allow each of my team members to showcase their own contributions to the project.
Hello, my name is Jourdyn, and this is my contribution to our malware analysis project. Before I dive in, I want to talk about how my role evolved. My original plan was focused on high-level project management and documentation. However, as we began, it became clear that building a secure analysis environment was a complex and critical first step, so my role deviated. I pivoted from project management to becoming a member of our technical team for building the sandbox and then performing a full end-to-end analysis on one of our key malware samples. This deviation was necessary because the practical needs of the project required a dedicated technical focus. My first major task was to build a secure, isolated environment. We used a virtualization platform like VMware Workstation for one critical reason: to create a sandbox. This is a safe, completely contained digital environment, a host-only network, where we can run dangerous malware without any risk of it infecting our actual computer or spreading across the network. For the guest operating system, I chose Windows XP because many malware samples are designed for older systems, and running them in their native environment is key to observing their intended behavior. This entire setup was designed to let us watch the malware while it performed its function. With the environment ready, I began analyzing my assigned sample. I started with static analysis, which means examining the file without running it. My first step was using PE Studio to get the file's basic properties and, most importantly, its cryptographic hashes. I then used this hash to query VirusTotal. We use VirusTotal because it's the fastest way to get a high-level consensus from the security community, scanning the hash against over 70 different antivirus engines. The results confirmed the file was malicious, and more importantly, that it was packed using tools like XOR Crypt and Armadillo. This told me the code was scrambled and the real secrets would only be revealed when we ran it. Next, I moved to dynamic analysis, executing the malware in the sandbox. For this, I used Process Explorer. We chose this tool specifically because it's a powerful upgrade to the standard Windows Task Manager. Its most important feature for our analysis is its ability to show a detailed process tree, revealing the parent-child relationships between all running processes. Using it, I saw this malware use a technique called process hollowing. It launches a legitimate svc host.exe process, replaces its memory with malicious code, and then terminated itself. This left the malware running hidden inside a trusted Windows process, a detail a basic Task Manager would have missed. I confirmed the process hollowing by using another great feature of Process Explorer, comparing the strings from the on-disk file versus the live process in memory. They were completely different. The memory contained keylogging artifacts like shift and enter. To confirm, I typed in a text editor, and the malicious process wrote every single keystroke to a log file, proving its primary function, as can be shown here. The analysis wasn't without its difficulties. The packed code made static analysis extremely convoluted. Because the malware was packed with Armadillo and XOR Crypt, its code was unreadable during static analysis. By pivoting to dynamic analysis, I could focus on observing its live behavior in the sandbox. The second challenge was the malware sample's stealthy execution using process hollowing. The malware hid its activity inside a legitimate svchost.exe process, making it difficult to spot. However, I used Process Explorer to analyze the process tree. The presence of an orphaned svchost.exe was the initial clue. I then confirmed the injection by comparing the on-disk versus in-memory strings, which were completely different. The third challenge was the legacy environment setup. Modern virtualization software doesn't fully support older operating systems like Windows XP out of the box. I overcame this through careful research, sourcing specific legacy versions of VMware tools and Hyper-V integration services from archives to ensure the virtual machine was stable and fully functional for analysis. The project was a fantastic learning experience. It showed me the critical importance of a properly configured isolated analysis environment, how malware uses packing and encryption to defeat static analysis, how dynamic analysis can uncover sophisticated evasion techniques like process hollowing, and how identifying indicators of compromises like orphan processes and unexpected file writes is crucial for real-world threat detection. Thank you very much.
Hi, my name is Jack Eyink, and in this presentation, I'm going to go over my contributions to the Malware Analysis Capstone project. So this is in the first couple weeks. Basically just went through and set up a clean, isolated Windows VM and created a snapshot so that testing was safe and repeatable. Here's just a screenshot of the VMware workstation. Got a couple different tools running inside of it. Okay, this was the next couple weeks in our progress report number 2, where we started to get into some static analysis. For this specific analysis, I used Kappa, which is a tool by Mandiant. It's basically an open source reverse engineering or just plain malware analysis tool. So here's the summarized results from Kappa. Have a lot of information here, so I'm not going to go through each line. But basically what's happening is the malware sample that we input into Kappa is hiding inside of a trusted process. It runs code in memory, and then it also carries another program inside itself. So that basically means it can read and write files, create processes, parse PE files, and then that allows it to quietly unpack and basically run a hidden payload. So progress report number 3, this is where we started to get into dynamic analysis. For my specific analysis, I used Process Monitor and RegShot, both pretty easy, simple tools that can provide you with some valuable information on malware. So here's just the different tools operating inside of my VM. This is the raw view of Process Monitor. Kind of a lot of different things in here. In my actual official report, I went through and applied a bunch of different filters to kind of, I guess, parse out the unnecessary information and bring to light the more important stuff. But it shows a lot of standard things like standard DLL and system file activity, which kind of fits the in-memory execution narrative that I started earlier. And then here is the RegShot diff file. This kind of just shows that there weren't any really new startup entries, but it did create a keylogger file. That's the main artifact that's left behind by this malware when it's run. So that is the analysis that I did. Pretty quick, pretty short, pretty sweet. Definitely learned a lot. It was great to use these different tools and had a lot of fun in the process.
I have here the VM setup, the slides I'll cover for this presentation, and this report that we've referenced throughout our progress reports. So the first progress report entailed basically just setting up the VMs. We all sort of did the same thing here. I would say my contribution is just to I noted the Hyper-V section since I went through that process initially, so I added that in the progress report notes, and in the VMware section I helped out with the network type just to outline the custom section, make that clear. So yeah, that's progress report 1, just getting it all set up. And on the teamwork side, I did the tour, the demo of the VM setup, so showing all of these setups and all that goes on with VMware. So for progress report 2, this was with Remnux, and I have the Remnux here. So this is the output. I already put the commands in, but this is the output that happens when you run on Lab 301, PE frame, and floss, and in the notes we see that. So that's noted here, and analysis, particularly XOR behavior for PE frame. Somewhere, yeah, here. And this is entropy, so that was outlined, and floss. They both contain strings, and this has strings as well, and yeah, this particularly noted the HTTP string, so that was for report 2. In terms of teamwork, I also filmed the live demo showcasing what our team generally did with Remnux. And for progress report 3, this deals with the my section was with Process Explorer, so we have here Lab 301, and this is in Process Explorer, particularly that tool, and it shows details such as the strings that we saw in the other Remnux tools, and other things here generally are good info. Another tool of Process Explorer is to show signatures, and we can see that Lab 3 doesn't have a signature, so that's valuable information and notable for malware, and this is all noted in the report as well, as we can see here. So yeah, that was generally my contribution to the project.
Hey, this is Matt Gallo, and I'm going to be going over some of my contributions to the malware analysis project. Week 1, we focused on lab setup and creating a secure environment for malware research, and that involved downloading VMware, creating a host-only virtual network, and then configuring a Windows XP virtual machine. And I have the steps documented here for that. So this was the setup for VMware up top, and then the setup for the Windows XP virtual machine. Week 2, we focused on static analysis. First, I configured a Remnux virtual machine, which is a Linux-based machine that comes with malware tools, pre-installed malware analysis tools, and then selected a malware sample and ran it through virustotal.com, and summarized the key information from the VirusTotal report. And then I also ran the malware sample through the Remnux strings utility, and then parsed and identified potentially malicious strings from that. And that output is here. So this is the output from VirusTotal, and just a summary of that output. It showed that it was a poison ivy remote access Trojan, and then the strings utility output was here, and that showed that there's some evidence of Windows persistence mechanisms, HTTP communication, and VM evasion techniques. And then I also created a summary of what static analysis is, some of the techniques and tools that are commonly used. And then week 3, we did dynamic analysis. For me, that involved installing Redshot, configuring Wireshark and iNetSim on Remnux, and then I used Redshot to take snapshots of the Windows registry keys before and after running the malware sample, and that generates a comparison report, and then I analyze the findings from that. And I also simulated internet connectivity using iNetSim and captured network traffic using Wireshark, and then analyzed the sent and received packets from Wireshark. And that output and analysis is here. So this is the output from Redshot. It showed that there were 4 values added, 7 modified, and then my analysis of those findings here. And then the output from Wireshark and my analysis of the queries that were made here. And that was my contribution to the malware analysis project. And to conclude, this project can be expanded to include more advanced malware samples, in-depth reverse engineering techniques, and the use of automated analysis frameworks to streamline investigations. The virtual lab could also be adapted for collaborative use, allowing multiple students to safely connect and work on the same network. And beyond the static analysis and basic dynamic analysis performed here, future work could progress into more advanced dynamic analysis and reverse engineering, enabling deeper insight into malware behavior, code structure, and evasion techniques. Over time, this environment could evolve into a permanent training platform for cybersecurity students, offering hands-on practice with both legacy and modern threats while continually updating tools and methods to match current industry practices. Thank you for taking the time to watch our presentation.